Hello everyone. As you will be able to tell in a few minutes, I have a cold, so I am recording our lesson for Chapter 9, and hopefully you'll find this easier to understand than you would be in class tomorrow. All right, so first question we have here is about critical values of Z. And critical values of Z, as we're doing hypothesis testing, one thing to keep in mind is we've got critical and observed values of Z and of T. And these critical values are the ones that are the cutoffs. They're the ones that tell us whether it's like the cutoff line between whether we're going to reject or fail to reject the null hypothesis. And as you've listened to the other videos, you've already been already aware that it's all about the null hypothesis. We only make a decision about the null, and that's what this is going to help us determine. So I've already explained that in our first videos that you've hopefully watched. So let's just do some examples and give us some practice in figuring out these critical values of Z first. The critical value for each of the hypotheses is listed. It's asking us to find a critical value for a left-tailed test for a proportion. Now, a critical Z value, of course, if it is a proportion, it has to use the Z table. You know that. They've given us a sample size, but that really doesn't matter too much in finding that critical value of Z for that proportion. What we do have to say is if this is the Z table, I'm going to draw a few of these so that you can get used to what we're talking about. This is the Z table. We've got a left-tailed test of the hypothesis. So we've got an area over here that the entire test of the hypothesis is in. In other words, all of alpha is over here. This is our rejection region. How big is our rejection region? Well, it's 0.05. That's the alpha, the confidence level almost, or the area we would reject if our test value fell into that area, okay? So what we have to determine is what is that Z-score that goes along with it. Well, you would look up 0.05, and as I told you before, you really only need the negative side of the table for this particular test that we're taking, because we're looking at the areas in the tail. Whether it's in the right tail or the left tail, we're going to use the sign, but it's just the areas in the tail. So those are always, the smaller areas, they're always going to be found on the negative side of the table. So I'm going to look up 0.05 on this side of the table, and I go 0.0, and I find it in here. This is really between these two numbers. So I would say I'm going to split the difference. I'm going to say it would be between a negative 1.64 and a negative 1.65. I'm going to call that, either one would work, by the way. You could use either one of those Z-scores, but I'm going to say 1.64, and then I'm going to add another decimal, 5. So I'm going to call this a negative 1.645. Now, if we were doing calculations with it, we would just use a positive Z always. But as far as where it's placed, it is a left-tailed test of a proportion, so a left-tailed test of a hypothesis, so it is on the negative side of our table. All right, let's look up another one. This one's saying critical Z value for a right-tailed test for a proportion, so it's also Z, of course. Sample size of 122, and alpha this time is 0.02. Well, let's do the same thing. Z-score, right-tailed test, that means that this area, we're always interested in the areas in the tail when we're doing these critical values, is equal to all of alpha. Once again, a one-tailed test, we put all of alpha into the rejection region. That's our rejection region. We need this score. Once again, though, we're looking up the area in the tail. Now, we could look up the opposite of it on the positive side if we wanted to, or we could just look it up on the negative side and take the positive Z-score. So that's easier. Let's go 0.02, and when I get to 0.02, I'm going to find out it's really, really close to these two numbers. It's right in between them, so I'll go between them again. I'm going to say 2.05, and I'll add another decimal, a 5. 2.055. You could have said 2.05 or 2.06. I use positive because I know it's a right-tailed test. It's on the positive side of my Z table. And that's how I can determine that. I always know that. Let's look at the next one. We have a critical Z value for a two-tailed test. This time, two-tailed test of the hypothesis means that we have to divide it up into two equal areas in the two tails. Both of these would be rejection areas. How big are they? Well, we take that alpha and we divide it by 2. Well, significance level of 2% means that alpha is equal to 0.02. That's 2%. So we have to divide it this time because it's a two-tailed test, and each tail would be half of that, 0.01. So when I figured out alpha was 0.01, all I had to do was go look up 0.01. 0.01, really, really close to this, isn't it? 0.0099. So I will call it 2.33, which would be over here a negative 2.33, and over here a positive 2.33. So I have two cutoffs. If my test statistic fell below a negative 2.33 or above a positive 2.33, I would reject. Those are my rejection regions. All right, let's take a look at the next one. This time we're going to be talking about t-scores. So let's practice, and this is really just practice, seeing if you can find these t-scores. The t-value such that the area in the left tail of the t-distribution is 0.005 and the sample size is 99. Now for a t-value, sample size 99 means that degrees of freedom is equal to 98, and you always have to know that, right? And then I want to say, okay, well, left tail, let's just call this our t-table. 0 is always the center. And the area in the left tail over here is our rejection region again. It's 0.005. This time I'm looking for a t-score though. So when I look for a t-score, it sort of helps me out. My table up here gives me the one-tailed test, right? 0.005 is the area in a one-tailed test, and this is a one-tailed test. But I need degrees of freedom. This time it was 98, so I got to go all the way down. It's not on this page. On the next page, I've got to all the way down to past 75. The infinity is where we'll use this one, okay? And so I've got what was the area is 0.005, which is the second column here. 0.005, one-tailed test, right? And I go all the way down to the very bottom, and I come up with my t-score here of 2.5763. Okay, I'm going to put it here. But look at where it is. It's on the negative side of the t-table, isn't it? It is a left-tailed. It's an area in the left tail. So I have to remember that I need to use the negative t-score, not the positive, okay? Let's look at the area value of t. So the area, this time in the right tail. Okay, if I draw it, t, area in the right tail is over here. It would be our hypothesis rejection region. And this area is 0.1. So sample size is 42. Degrees of freedom would be 42 minus 1, or 41. This time I'm going to be looking for 41. I look at this row, 41. And the area I'm interested in was, what was it? 0.1. I look for the 0.1, and here it is. So 41.1, I've got a t-score of 1.3025. 1.3025. Should it be positive or negative? Well, it's on the positive side, on the right side, so I've got it right already. It's a positive t-score. I think I've got one more of these for you with the t-table. So we have two values of t, and this time it tells us that 95% of the area under the t-distribution is centered around the mean. It's a good idea to draw these things. 95% is centered around the mean, right? So in other words, if we center this around the mean, which we always know is in the middle, this is equal to 0.95 of the curve, of the total curve. 95% is centered around the mean. Sample size is 32. We know it's a value of t. I'll go ahead and say, okay, degrees of freedom is 31. But then I've got to look at my areas here and here. Well, how big are they? Well, they have to be 1 minus 0.95, which is 0.05, isn't it? And I take that area and I divide it by 2 because I'm splitting it. One on each side. I have a rejection here, rejection region here, and I get 0.025 in each tail. I've only got to figure out one of these because they'll be opposites of each other. One will be positive, one negative. But if I look up a one-tailed test of 0.025, what is my one-tailed test? I'll just look up one tail of it. 0.025 with degrees of freedom 31. Degrees of freedom is 31. What did I say? 0.025 would be, if it was a one-tailed test, it would be here. If it was a two-tailed test, it would be just above it. So I'm in the right column, either way you want to look it up. I always prefer just to think about what one tail is going to be. And here it is. This column, it should be 2.0395. Well, that would be 2.0395. And over here, a negative 2.0395. And that will hopefully give you a little practice in looking up these different t-scores and z-scores, the critical values. Now, another thing that we've got to be able to do in this chapter is to calculate or to determine something called the p-value. The p-value is the area in the tail past the rejection, past the test indicator, where our sample test tells us it's our sample test determines. Sorry, I do have a cold. So we're going to look at a couple of examples just to see if we can practice doing that, finding that p-value a little bit. It says to calculate the p-value for a given hypothesis test, rounding it to 4 decimal places. We're going to find the p-value for a left-tail test of hypothesis for the mean when the test statistic has been calculated as negative 2.16. The population standard deviation is known. Therefore, because it is known, the test statistic is a z-score. What they just told you is that z is equal to negative 2.16. It was a left-tailed test, so you knew it had to be negative. The one thing you didn't know was whether it was a t-score or a z-score. But here is our rejection region. What we know that rejection region has a test value, which is called the critical value. The critical value is a negative 2.16. What we don't know is how big this rejection region is, but we can look it up. We can look up a negative 2.16 on our z-table and find out how big that is. Negative 2.1, and I go over to 6, 0.0154 is how big that area is. That is the p-value, okay? The p-value is the area in the tail past the critical value, whatever it is, z or t. Sorry guys, if you haven't figured it out, I'm having to stop this tape every now and then so that I can cough and sneeze without blowing your eardrums out. So just bear with me, okay? We'll get through this. So that's our first example. Now let's look for a p-value of a right-tailed test of the hypothesis. And this is a test of the proportion. So when you do a proportion test, you should know that's always going to be a z-test, okay? So this is also a z-score that we're dealing with. Sorry, the test statistic, which would be our z-score, has been calculated to be 2.21. They want the p-value. They want the area in the tail, okay? So this time it would be the area in the right tail because it's a right tail test. We're still going to look it up on the negative side because that would give us the area in the left tail, and we would just say, okay, that's the same as the area in the right tail, right? So I'm going to say 2.21. Here it is, 0.0136. So it is this time 0.0136, and that's the p-value. The p-value is one way we do compare and do hypothesis testing. We compare the p-value to alpha. If p-value is less than alpha is always the test. Now let's do a two-tailed test of hypothesis when the test statistic has been calculated as negative 1.68. Population standard deviation is known. That tells us this is a z of negative 1.68, okay? Now this is a two-tailed test of the hypothesis. So what I want you to do is think about it like this. Negative 1.68 would have been here, but it was a two-tailed test, so there was a positive 1.68, right? So really, we have an area, a rejection area in both sides. Let's look up that negative 1.68 and see how big that p-value is, or how big that area is. 1.6, and I go all the way over to 8, and I go 0.0465. That's how big this one is. But think about it. This is a two-tailed test. When we have p-value and we have a two-tailed test, we take the area and we multiply it times 2. So p-value for this one is equal to the area in one tail times 2, which would be 0.093. So that two-tailed test of the hypothesis, just remember, you find the area in one of the tails, multiply it by 2 because it is a two-tailed test. And that's what you have to compare to alpha to see if you reject or fail to reject the null hypothesis. Now, this one, the work has already been done for us in question 4. It says we have a hypothesis test for a proportion, and it was alpha is equal to 0.06 was the test we were doing. The p-value was calculated to be 0.0306. So they already found out what the z-score was. They found the area in the tail to be 0.0306, okay? It was a one-tailed or a two-tailed test, whatever. They've already calculated the p-value. We want the conclusion. Now, what you have to remember is that the test is p-value less than alpha. That's always the test. P-value less than alpha. Is p-value less than alpha? If p-value is less than alpha, then we reject the null hypothesis. So what you have to do is say, well, p-value is 0.0306. Is that less than alpha, which is 0.06? And we look at that and say, well, yeah, it is, isn't it? So this one would be definitely less than 0.06, so we would reject the null hypothesis. So let's take a look at number 5. Says we have a left-tailed test, a hypothesis test for a proportion. So that's going to say our z table is going to be what we use. And the test statistic for the hypothesis was calculated to be a negative 1.65. So what they're saying is z is equal to a negative 1.65. Test statistic, that's the one that was determined from alpha, right? So what we want to do is let's draw it out, see what it looks like. We've got a left-tailed test. Our rejection region will be over here, past a negative 1.65z. I put down standard deviation is known, but that's not true for proportion problems, so ignore that, okay? Determine the correct conclusion given the result, and the significance level that we're interested in is 0.1. In other words, alpha is equal to 0.001. Remember, 0.1% is not 0.1. You have to still move it 2 places, so it's 0.001. So what we really want to do is we want to do a p-value test, right? We know what alpha is. We know if p-value is less than alpha, we will reject the null hypothesis. So let's see if we can find out what the p-value is, and that's associated with this negative 1.65. I'm going to go to negative 1.65 and find out what p-value is. There it is. It's 0.0495. So p-value is equal to 0.0495, and you have to ask yourself, is 0.0495 less than 0.001? That's our test. Is p-value less than alpha? Well, that's not less than. So this one doesn't reject. This one fails. We fail to reject the null hypothesis. Okay, we don't say we accept it, but it probably has merit, okay? That's what we usually say about that. Now, the next one I've got for you here, number 6, says we have a right-tailed test for mean. The test statistic was calculated to be 0.7014. Came from a sample of size 30. But the other thing I want you to note is that the population standard deviation is unknown. In other words, This is a t-score, okay? It's not a z-score this time. So let's kind of draw this out. This is the t curve. It's a right-tailed hypothesis test. Goes over here. And it says t is equal to 0.7014. That sounds like an area, but it's not. It's the test statistic. Now this time the sample size of 30 does mean something to us, because that means that we have a degrees of freedom of 29. And we're going to have to look up that t-score and see what this area, this rejection area is, because that's our p-value, okay? Now it's kind of a little tricky when you've got the t-table, it's different. But pay attention to this. You see that degrees of freedom, 29? That's the only row that you are allowed to use in this table. For that problem, degrees of freedom is the first item that you have to look up, and you have to stay with it. I've got this degrees of freedom 29. That's the only row I can look at. What am I looking for? Well, I'm looking for a t-score of 0.7. These are all bigger than 0.7, aren't they? So it's going to be over here to this side, way to the right. Therefore, when I look at my one-tailed test, these numbers are getting bigger, aren't they? These areas are getting bigger as they go to the right. All I can say for certain is it would be bigger than 0.1. I know that's where it would be. So it's going to be greater than 0.1. I don't know how big that area is exactly. I can find it exactly if I want to go in maybe and do it with a calculator, but this is good enough. Greater than 0.1. So I'm going to do my comparison here. I'm going to say is p-value less than alpha. Well, alpha is given to me right here, 0.05. I'm going to just fill these in. 0.5, right? The p-value, what is the p-value? Well, the p-value is going to be greater than 0.1, right? And this has to be less than 0.5. And at this point is greater than 0.1, less than 0.5. It would be really almost impossible for us to tell if this rejected or not, okay? I picked really bad numbers here, so I'm going to pick a different set of numbers and show you how it would work out if we had a more definitive answer. And actually, in my notes, I had changed this, and it was supposed to be 0.05. So why don't you change it to 0.05? Okay, because that made it a definitive answer for us. So if I've got p-value, which had to be bigger than 0.1, but to pass the test, it has to be less than 0.05. It's not going to pass the test, is it? So it's really going to fail to reject. And hopefully that didn't confuse you too much. Okay, just change those numbers to 0.05, the alpha level, and then you can see how it would fail to reject. Okay, number 7, we're going to take it just a little step further and start putting all these things together as getting ready for our hypothesis test. We have been given a two-tailed hypothesis test for a mean. It has, it's saying round any z-scores to 2 decimal places, t's to 4, and it's telling us a bunch of stuff. But let's see if we can set up a two-tailed test. We don't know if it's z or t maybe at this point, but we do know that the rejection region is in both tails, okay? I'll just go ahead and put it up there. These are the rejection regions. The significance level of the test is 0.1. So what we know here is that alpha is equal to 0.1, right? 10% is 0.1. The sample size is 48. Population standard deviation is not known. So we're going to have to go with the t-table, and that sample size becomes important. Degrees of freedom is 47. This alpha, because it's a two-tailed test, has to be divided by 2. So it's 0.1 divided by 2, which would give us 0.05. And that would be the rejection area in each tail. And let's go ahead and put down now that we know it's a t-test. Now, we got to look up these t-scores because that's what they want us to find. We'll find our t-score by going to degrees of freedom 47 on our t-table. And as I told you before, you can go to 0.1 as a two-tailed test, or you can just look at one tail of it as 0.05. It's going to be the same column. And you should get 1.6779. 1.6779, and negative 1.6779. So you've got two rejection regions, therefore you have two critical values. We would reject if it was below negative 1.6779. We would reject if it was above a positive 779. Sorry, I think I got that right, didn't I? Let me make sure I'm copying these down. Okay, very good. Next, we're given that we have a left-tailed hypothesis test. I'll go ahead and put the rejection region in the left tail. And it has the given characteristics of a significance level of the test is 2.5%. So alpha is equal to 0.025. It's just a left-tailed test, so all of alpha goes in there. We don't have to divide it by 2. The sample size is 48. The population standard deviation is known. Therefore, it is a z-test is what it is, okay? So we've got a z-test, and we need this z-score, and we have the area. So we're just going to go to the z-table, negative side as always, right? And look up 0.025. You may remember this one because we've looked it up a lot. 1.96 on the negative side is negative 1.96. And that is our critical level. That's our critical index, our critical test. Okay, with problem 9, we're going to start putting all of this hypothesis test practice that we've been doing together. We have a car battery manufacturer says that its car batteries last 3 years on the average, but many customers have had failure before 3 years, so there's a consumer advocacy group, and it's investigating to determine if the average lifespan of the car batteries is exaggerated, if it's misleading. They're going to be looking for it being less than 3 years. They take a random sample of 62 batteries. We'll start writing stuff down here. N is equal to 62. They were tested, and they found that that mean lifespan, which would be the sample mean, because it's the mean of that sample they took, was 2.81 years. We're going to do the critical value method. We're also going to do the p-value method. We're going to do both, okay? To test the hypothesis that the mean lifespan of this brand of car battery is less than 3 years. So what's the test we're running? That would be H1. The mean is less than 3. So what's the null hypothesis? Well, that's going to be the opposite. The mean is greater than or equal to 3. Now you should remember, equal never goes in the alternative, but it always goes in the null. So we'll have equal up here always. We will never have it down in the alternative. The alternative hypothesis is what we as researchers are interested in. The researchers in this case are the consumer advocacy people, and they want to know if the mean is less than 3 years. In other words, is the company cheating people, okay? They're going to use an alpha level of 0.03 because that alternative hypothesis has a less than sign, and we know that this is a and we know the standard deviation is known. Where does it say? The standard deviation of the lifespan of all batteries, that's the population standard deviation, is known to be 0.25. We're going to use the z-table. And that's the reason right there, because we know the population standard deviation. Otherwise, we would be using the t-table. So what do we know? Well, we know this area right here. We know this rejection area is going to be 0.03, right? That's going to be my rejection area. This right here is my critical value of z. I don't really know what that's going to be yet, but I can look it up. I can find out what it's going to be by looking up that 0.03. No, I'm going to say this is my rejection region. Let's go ahead and find that 0.03, okay? 0.03 is going to take me right about here. I'm going to use this one. I'm going to use a negative 1.88. So this would be negative 1.88, filling in all the blanks. That's my critical value of z. If the test statistic, when I run the test, if it falls below negative 1.88, in that 0.03 that's over there in the left tail, I will reject the null hypothesis, okay? So what do I assume? Let's see, I want to next calculate what the observed value for z is. Now the observed value for z is calculated very much like we've been calculating our z-scores before. We're going to take the test statistic, which they ran to be 2.81. And I'm going to say observed Z, which is the test always that we ran, is 2.81 minus the mean, which is right here in the center, right? If I were to write it down for you, it would look like this. There's the mean, what they said it was the mean. That's the one I'm comparing it against. So I'll say 2.81 minus 3, and now I have to divide by this, not the standard deviation that's given to me, but the standard deviation of x bar. I have to take, and I always have to do this with hypothesis testing, and divide it by the square root of the sample size. So I'm going to take 0.25, and I'm going to divide it by the square root of 62, and I'm going to go to 4 decimal places. You should always do that with these standard deviations, and come up with 0.0318. So what is the observed value for Z? Remember, we've got two Z values. We've got the critical Z, and we got observed Z. Observed Z has to do with the test that we ran, the sample that we took. And it came out this time to be a negative 5.97. Now, where would that fall? Well, negative 5.97 is off the charts, isn't it? Over here, let's just put it, negative 5.97. Going to be over here somewhere. What would the p-value be associated with a negative 5.97? Now, you can tell it falls into the rejection region, right? We are going to reject the null hypothesis, is what we're going to do. It does look like the consumer advocacy group has merit in their claim that a company might be not truthful on their average life of the batteries. But what's the p-value test? Well, we don't even have negative 5.97 on the Z chart. So you know that this area is really 0. So what is p-value here? Well, p-value is equal to 0. Is p-value is 0 less than alpha? Which was alpha? What was alpha? 0.03. And you would say, yes, it is. So what do? Reject. P-value tells you to reject. The critical value, the test statistic that we ran, tells you to reject based on the critical value. And so it passes on both counts. And that's kind of what you should be able to do. You should be able to do both of these tests on any problem you're given. That way, any way you're asked the question, you can answer it. Okay, let's take another one sort of like that. It says Rust-Oleum is a company that manufactures and sells paints. And their spray paints are supposed to contain 12 ounces of paint per can. But every 1.5 hours, quality control selects a sample of 20 and carefully weighs them to ensure that each can has 12 ounces on average. Now, if this mean is found to be sufficiently different from 12 ounces, they have to shut down their line and inspect it. So they took a recent sample of 20. You could say, okay, there's my sample size. And they found the recent sample, the mean weight for that sample was 11.85. And with a standard deviation. Now look, we're talking about sample mean, sample standard deviation, right? And that's important. We don't know the population standard deviation, do we? And since we don't know the population standard deviation, this right here tells us you have to use the t-table. If you try to use the z-table, you'll miss the problem, okay? So a standard deviation of 0.46. We're going to test the hypothesis that the mean weight of this is different from, now there's your test, is different from 12 ounces. So what are we testing? Well, our hypothesis is that the mean is not equal to 12. Now, not equal could be higher than 12, could be less than 12. That means is different from. So what's the null? The opposite of that. The mean is equal to 12. And that's the way those are set up. Now, if we have a not equal alternative hypothesis, we have a two-tailed test. We have a rejection region in both tails. We know it's a t-test. It's a good idea to write that down so you don't get busy doing the problem and forget. We also know that we still have to adjust every standard deviation by dividing by the square root of the sample size. We might just go ahead and do that. Standard deviation of x bar. In this case, we would take 4.46 and we would divide it by the square root of 20. And we'll go to 4 decimal places with all of our standard deviations. That'll help us make sure we get enough precision in our problems. And that's what I come up with. Now, how big a rejection region do I want here? Well, I have to see what the significance level is. Significance level is 0.01. Therefore, alpha is equal to 0.1%, which is 0.001, isn't it? I've got to divide that by 2 because I have a two-tailed test. So alpha divided by 2 is going to be half that, 0.0005. I think that's right. And we're going to go to degrees of freedom what? Degrees of freedom is 19, isn't it? So that's the first thing we always have to know when we're looking at our t-table is what's the degrees of freedom. Degrees of freedom 19, and alpha divided by 2 of 0.0005, or you could say one-tailed test of this, two-tailed test of that, either way. Where's our degrees of freedom 19? And I always go for the one-tailed test of 0.0005. Here it is. It's right here. It's going to be 3.8834. Now, I know I have a positive and a negative, negative 3.8834, and this would be a positive 3.8834. Now, my test could be, the spray cans, the samples could be higher than or it could be lower than. If it falls into either of these regions, we would reject. So let's find out where our test statistic fell. We took our sample, that's our observed value of t, and we took it, our sample came out to be 11.85. We'll subtract what we thought the mean was. The mean that you're going to subtract is always going to be in the hypothesis statements, okay? And divide by the standard deviation that we adjusted. And we come up with observed t should be equal to a negative 1.4577. Now, we don't need the positive side at all, do we? Because we ended up with a negative test. So our negative, where does it fall? Well, it doesn't make the cutoff, does it? Negative 1.4577 is over here. It's not going to make our cutoff here, is it? So, but if I wanted to look at what the p-value for that was, I would look it up. Now, once again, the p-value is not so easy to necessarily look up on the t-table. What you have to keep in mind is that you can only use that one row, degrees of freedom 19. So I'm going to go to degrees of freedom 19, and I'm going to try and look up my observed value of t, 1.4577. Just ignore the negatives for this table. And when I find it, it's going to be right between these two columns. So I go up to the top of those last two columns, and I say this is the area. For a one-tailed test, this is actually a two-tailed test, so I can go up here and say between 0.1 and 0.2. Now, this area is going to be between 0.05 and 0.1, right? But we would multiply that times 2 to get p-value, and that you can almost just go up and read two-tailed tests because they've already done the multiplication. So what is the p-value? P-value is going to be between 0.1, somewhere between 0.1 and 0.2. Alpha, however, where's our alpha? Alpha is 0.001. Is p-value less than 0.001 is what you're asking yourself, and no, there's no way it is, right? So what happens? Well, it fails to reject the p-value test, but it failed to reject the critical value test too. Question 11 says that there's a physician that wants to see if his patient is at high risk for maybe at risk for high cholesterol, and so he's going to check his cholesterol level, and he's going to do it once a week for 11 weeks, and then he gives us the actual test results. Now, you don't have to worry about whether you have sample data or population data because this is the sample he took, right? This is 11 weeks. He took samples of the blood lipid screening for 11 weeks, and that's the sample data. We want to use the critical value method, and we'll also talk about p-value, to test the hypothesis that the patient's cholesterol level is, and here's the hypothesis of the physician, greater than the dangerous 195, okay? So I'm going to come down here and say N here is however many he took. 1, 2, well, he did 11 weeks, right? N is equal to 11 here. isn't it? And then I'm going to say, do I have a sample or do I have a population standard deviation? Well, I'm only going to have a sample because I only got sample data. I don't even know the sample mean. They didn't tell me. They told me that they wanted to check in an alpha level of, what was it, 0.05 is my alpha. And I know I've got to be a t-table. Now, why do I know a t-table? Because all I've got is sample data. That means when I get the standard deviation, it'll be a sample standard deviation. I'm going to go ahead and put it down here that this is a t-table I'm working with, okay? Just so I don't forget. Now, the first thing I've got to do is get the sample mean and the sample standard deviation. And the easiest way to do it is, of course, going in and putting it into, let's see if I can do this so you can actually see it. That's not going to be easy. Maybe if I turn off this lamp, or turn that lamp on, that might help. Okay, I think I got it now. So if I say edit, and I can enter the actual data values into a list. List one's empty, so I'll go 185 is the first one. And then I've got, what, 186, 198, 199, 198, 197, 206, 186, 204, 200, 204. It's always a good idea to check these things after you put them in there. 186, 198, 199. Okay, so it looks right. Hopefully I got them right. And I have 11 of them. And now I can go ahead and do stat and calc one variable statistics. List one, there's no frequency list. And there it gives me my sample mean and my sample. Note, you only want to use the sample standard deviation. So I need those two things. I'll say the sample mean came out to be, let's see, 196 point, and I'll go to 2 decimal places. I would round it to 64. And the sample standard deviation came out to be 7.6062. And that's what rounded to 2 decimal places it gave me, okay? Now, it told me I had an N of 11, which I already knew. I know alpha here. I've got to figure out where my test is going. He wants to know if it's greater than. Let's go ahead and write the hypothesis statement. He wants to know, here's what the doctor wants to know, if the mean is greater than the 195, right? What's the alternative? I mean, the null hypothesis would be that the mean is less than or equal to 195. So it would be the middle, 195, right? So we have the sample standard deviation. If you don't have the calculator, you're going to want to go back into chapter 3 and do those by hand. And there will be a problem like this on test 4, but you won't have too many data values. You will have time to do it by hand if you have to. So we're going to take this 7.6062 and divide it by the square root of 11 here. And when we do that, we get a standard deviation of 2.2934. That's what we'll use when we calculate. Now, we really ought to be able to set up our alpha, our rejection region, okay? It was a right-tailed test because of this alternative hypothesis. We want to know if it's greater than a certain number. And this area that we're interested in is area 0.05. That's our rejection region. It's in the t-table, so we've got a degrees of freedom, don't we? Equal to 10. And that's the only row we can use. Let's go to degrees of freedom 10 on the t-table, and let's see if we can find that 0.05 in a one-tailed test. Where is it? Right here, next to last column. So I come up with a t-score of 1.8125. There's my t-score. That would be my critical value, that's my cutoff value. All right, so let's calculate what the observed value is, see where it falls. Observed value of t is going to take my test that I did, the sample mean, subtract what's in the hypothesis statement, which is the 195, and divide it by the standard deviation that I had to adjust. I come up with 0.71 0.7151, okay? 0.7151. And where would that fall? Well, it's not as big as 1.8. It's going to fall somewhere in here, 0.7151, isn't it? And so it looks like it fails to reject, doesn't it? Now let's look at the p-value of it, just for practice. I'm going to look up 0.7151 on degrees of freedom 10. Remember, if you're using the t-table, you cannot go off of the degrees of freedom. They are the measuring stick for everything, okay? So I've got 0.71. Let's see, where would 0.71 be? Well, it's going to be smaller than this number here. So it's going to be over here. If I'm looking at the area for a one-tailed test, these areas get bigger as they go to the right. So over here past, it's going to be greater. All I can say about it is it's greater than 0.1. All right, so my p-value, well, I'll write it up here, sorry. P-value over here is greater than 0.1. Well, what was the alpha? The test is p-value less than alpha. It's always the same. Well, is this p-value of bigger than 0.1 less than 0.05 is what you're asking. And no, it's not. So it fails to reject there too, okay? And so it fails both tests. You just need to be able to understand and do that rejection for both tests, okay? Next, we're going to look at problem 12. It says that certain electric cars were reported to have an average range of 213 miles, but there's an auto industry journalist who wants to verify it. She believes that the range may be less than that. So she tested a sample of 111 cars. And she found the average range of this sample was 202.2. So that's her sample mean, isn't it? And there was a population standard deviation of 34.7. That population standard deviation tells us that we get to use the z-table. So we're going to do the p-value method. We'll do the critical value too, and we're going to test the hypothesis. The hypothesis is the average range of this electric car is less than 213. That's the alternative hypothesis. That's the one she is testing. Less than 213. So what's the null? The opposite of that. The mean is greater than or equal to 213. So there's our hypothesis statements. We have a left-tailed test because we are testing less than, okay? The area alpha is a significance level of 5%, so alpha is equal to 0.05. Since it's a one-tailed test, we can put it all in one tail, and that's our rejection region. Now, it said do it with the critical value. Well, that's going to be find the z-score for 0.05, isn't it? But this is what we have to do anyway, even if we're looking for p-values. So 0.05 would take us right about here. I could say 1.64, 1.65. Whoops. I'm going to say 1.645. I'm going to give it another decimal place, negative 1.645. Why negative? Because it's a left-tailed test. It's on the left side of the curve. Now, I've got everything set up. I know I've got to calculate my observed value for z. I know the sample, but I know I have to have the standard deviation of x bar, right? So I'll take 34.7, divide it by the square root of that sample size, and this time I come up with 3.2936. So now I can say my observed value for z is going to equal my sample mean minus the mean that I'm comparing it against, the one that's always in the hypothesis statements, right? And I'll divide by a standard deviation, always the one that I have to calculate. And here I come up with a negative 3.28. Where is that? Well, negative 3.28 is over here somewhere. Way over here, right? Definitely in the rejection region. What if they ask you the p-value for this test? Well, you look up negative 3.28. Where is it? Negative 3.28. And you have a p-value of 0.0005. Is p-value less than alpha? Alpha is 0.05. That's definitely less than 0.05. So it rejects on both terms, on both tests rather. Now for the last two problems, we're going to move into proportion questions. Proportion problems always use the z-table. So if it's a proportion problem, you don't have to worry about whether it's t-table or z-table. It's always going to be z. How do you know it's a proportion problem? It talks to you about percentages. Also, it doesn't give you a standard deviation at all. I mean, not even a sample that you calculate it from. It gives you percentages, and you have to have the p hat and q hat, or p and q, and you calculate your own standard deviation of the sample proportion, okay? We've got a virus that's taken root in a country, and government officials are reporting that 6.5% of the population is infected with it. However, epidemiologists think that it could be much higher. So let's see what the government says. Well, the government says they think the population proportion here, they think that population proportion is 6.5%. Write it as a decimal, okay? That's what they think it is. They sampled 1,000 people and found that out of that 1,000 people, 85 were infected with the virus. That's their sample proportion, isn't it? Sample proportion is there were 85 out of the 1,000 infected with the virus. If we did that as a decimal, there's our sample proportion, isn't it? Now, we have to come up with a standard deviation to use in our calculations. And the way we do that standard deviation, check your formula sheet to make sure you've got the right one. Okay, make sure you can find this. I just wanted to pull it up so you could. Here it's saying the standard deviation of p hat is equal to p times q divided by n. Now, it's not the sample. That's the population proportion times q divided by n. So because in these problems, you're going to have a population proportion and a sample proportion. Which one do you use when you calculate the standard deviation of p hat? We use the population, okay? And if you ever doubt it or question which one to use, check your formula sheet. If p is 0.065, q is 1 minus 0.065, isn't it? You type that into your calculator, so because that's not one you probably want to do in your head, and it would be 0.935. So I'm going to take and calculate my standard deviation by saying p times q divided by n. Now look, all of this is under the radical sign. So if you've got to put parentheses in your calculator, make sure everything, you end it with parentheses. Otherwise, it'll just take the square root of the first one. So you would say square root, paren, all of this included, p times q divided by n, close your paren, so everything is under the radical. And when I do that calculation, I get 0.0078. Be sure you take it to at least 4 decimal places. I'm going to go ahead and put my hypothesis down. I should have done that before. The hypothesis, the null, and the alternative. The alternative is that they think the population proportion is greater than 0.065, okay? That's what they said. They think the true rate of the infection is higher than 6.5%. So that's what the epidemiologists think. The null hypothesis would be the opposite of that it was equal to or less than 0.065. Remember, we talk in percentages, but we always represent them as decimals when we do the math, okay? Now, how does this look? Here's our z-table, and we're going to be going less than or equal to something. We're going to be doing a left-tail test, aren't we? So I'm going to say, how big is it? Well, the significance level is our alpha, and alpha is 0.025. That's our rejection region. And from that, we can find our z-score. Z-table again, 0.025 is one we've done a lot. It is 1.96, isn't it? This is a negative 1.96. Over here is a left-tailed test. And now all we have to do is find our test statistic. We took a sample that came out with 0.085. So let's take and find our observed value of z. In other words, what did the test tell us? And the test told us that the sample proportion, 0.085, minus the population proportion, which is what we're comparing it against, divided by that standard deviation that we calculated, came out to be 2.56, didn't it? Well, 2.56 is way over here, isn't it? Okay, hopefully you've caught my mistake. I just caught my mistake. Guys, it's not a left-tailed test, is it? It's a right-tailed test. Sorry about that. I can only tell you that I have a cold. All right, how do I know it's a right-tailed test? Is higher than would be a right-tailed test. Also, look in the alternative hypothesis. It's pointing toward the right-tailed test, okay? So hopefully I've straightened that out for you. Z-score would have been calculated exactly the same way. We just looked at this area. We used the positive version because it was a right-tailed test. And now we're going to say, where does 2.56 fall? Much better. Looks much better, doesn't it? Well, 2.56 falls over here somewhere. So yeah, we're going to reject this null hypothesis, and we're going to say, yep, the alternative that the epidemiologists are saying, we think the rate of infection is higher than 6.5%, yep, it probably is true. What would be the p-value for that test? Well, all you do is go to the z-table and look up 2.56. Now, we're looking at the tail, so we're going to look on the negative side. 2.56 is 0.0052, isn't it? Is that right? So what do I got? 0.0052. I think I got that right. Okay. And is p-value less than alpha? Is 0.0052 less than 0.025? Yes. So it does reject the null hypothesis. Okay, for our last proportion problem, let's talk about COVID-19. Let's see. Reports from the U.S. Centers of Disease Control estimated that approximately 32% of those infected with the virus were asymptomatic or showed no symptoms. The rate of asymptomatic infections is important because we can spread it, and we know this. And then they took a sample of 575 and found that the infection rate was 33.5 that were asymptomatic. They want to do an alpha test of 0.01, and they want to test that the proportion of all people infected is different from 32%. Is different from 32%. Let's write down our hypothesis, okay? Hypothesis alternative is what they want. They want to say that the population proportion is not equal to 0.32. What would the null be? The population proportion is equal to 0.32. It's a proportion. It's a z-test. And we have a two-tailed test, don't we? A rejection region here and a rejection region here. Now, what are our rejection regions? How big are they? We're going to do an alpha of 0.01. So because it's a two-tailed test, we have to divide that by 2, and alpha divided by 2 is 0.005. When I've got 0.005, I can go to my z-table and figure out what my z-score is. What is my critical z? 0.005? Well, really between these two, isn't it? I can split the difference. I can say 2.575. I'll add another decimal place. And a negative 2.575. If it falls into either of those rejection regions, I will reject the null hypothesis and say that my idea has merit to it. So what else do they tell me here? Well, they've got to give me something about the test statistic. They estimated 32%, but they found that 33.5 of a sample is size 575, and they said that sample p-hat is equal to 0.335. Now, what's the population proportion that I want to run with? Well, I want to go with whatever they estimated, 32%. So Q is 1 minus 0.32, it would be 0.68. And now I can take these things, and I can calculate my standard deviation of p hat. Oh, I'm sorry, guys, you can't see a thing, can you? And that's equal to the square root of p times q, and it's divided by n. Don't forget, it all has to be under the radical sign. You should come up with 0.0195. Let's calculate now what our test statistic is. The observed value for z is going to equal whatever we said our sample was, came out to be 0.335, minus the population proportion, what we think it is, what we think it should be, and divide it by the standard deviation that we calculated. And we get 0.77, okay? Well, it didn't come out negative, so this side of the test is not useful to us. But over here, we got 0.77, didn't we? 0.77 doesn't go past 2.575. It's over here. It looks like it fails to reject. It failed the rejection. We can tell what that p-value is going to be if we look up 0.77. 0.77 on the negative side, of course, and it would give us 0.2206. That's what it is. You can't see both of those. 0.2206. That's how big that p-value is. The test would be, is p-value less than alpha? Well, ask yourself, is 0.2206 less than 0.005? And it's not, so it fails that test also. It failed to reject on both fronts. I'm very sorry that I can't be with you guys today, and I also apologize for having to stop this tape to cough and sneeze, but hopefully you've gotten a good look at some examples, and I'll be in virtual office hours on Sunday if you need me, and we will cover a review when I see you again next week.